Hello guys, it's great to see you here. I hope you are ready for an insightful discussion on binomial distribution function. In the previous lecture, we learned the Bernoulli distribution that represents a single experiment with two possible results, like success or you can say 1 and failure as 0. And common examples for Bernoulli distribution include tossing a coin that we have heads or tails, or determining the outcome of a test like pass or fail, or a binary event like yes or no. In today's lecture, we want to study binomial distribution. The binomial distribution is a fundamental discrete distribution in statistics, and it is somehow extending the Bernoulli distribution to multiple trials. This tutorial covers the definition of binomial, properties, mathematical formulation, and also practical example with Python code. First, what is binomial distribution? Binomial distribution models the number of successes in n independent Bernoulli. In here, we have two outcomes, one as success and 0 as failure. And for success, we have probability of p, and for here, we have probability of 1 minus p, right? So we have n independent Bernoulli trials. For example, counting heads in multiple coin flips, or the number of defective items in a batch. So here, n is always greater than or equal to 0, and probability of success is always between 1 and 0, right? The PMF of a binomial random variable, if we have a random variable of x, then we say px is equal to k. It's equal to combination of n and k, probability in power of k, and 1 minus p n minus k. In here, k is the number of success. Number of success, right? And this k can be from 0, 1 up to n, right? Because maximum we can have n. And this n and k is combination. So n and k is equal to n factorial divided by k factorial n minus k factorial. This is called as binomial coefficient. The binomial distribution, we write like this: x, this is a random variable, follows binomial distribution. We write binomial, and with parameters n and p, right? So we read this one as x follows a binomial distribution with parameters n and p. This models the number of success n independent Bernoulli trials, and each one has a probability of p. Next, we go for cumulative distribution function, or CDF. CDF, so this was PMF. CDF for binomial random variable like x is defined as the probability that x is less than or equal to a specific value x. We write in this way: binomial of x with n and p parameters is equal to probability that x is less than or equal to x, which is sum of y is equal to 0 to x, binomial of y, n, and p, and x is something from 0, 1, to n, right? So this b, y, n, and p is this one is simply, so we can write here b, y, n, and p equals combination of n and y, p in power of y, and 1 minus p in power of n minus y. This is the CDF for binomial distribution function. Next, we will go for the mean expected value of binomial. The expected number of sixes is simply AX is equal to N multiply P. This is derived from the fact that each trial contributes P sixes on average, and there are N trials. Then for variance, the variance measures the spread of distribution. So in here we can say var x is equal to np 1 minus p. And if we consider this 1 minus p as q, then we can say np and q. This 1 minus p is the probability of failure. And the variance reflects the variability across n independent trial. And then for a standard deviation, simply we can say sigma x is equal to root square of variance, which is root square of npk. This provides a measure of dispersion in the same unit of Sx. And again, this q is 1 minus p. So the binomial distribution, as I said, it is the sum of n independent Bernoulli trials. For example, we can say x is equal to x1 plus x2 plus up to xn, and each x follows in here, each x follows a Bernoulli distribution. So we can say xi follows Bernoulli of with probability of p, and if n is equal to 1, then binomial is the same as Bernoulli distribution. If we have a large n and p not too close to 1 or 0, then the binomial distribution can be approximated by normal distribution. We can say follows a normal distribution. Normal np and np 1 minus p. Now let's try some Python coding. Then again, we will come back to here for examples. So we want to try binomial distribution. First, we will import some libraries like NumPy, import NumPy as np, and also we will import Matplotlib, Matplotlib.pyplot as plt. Then we from SciPy SciPy.stats, we will import binom. This is available in SciPy. Next, we will set random seed for reproducibility. So we say np.randomSeed, and here we say 42. Then we define the parameters. N is equal to 10 as the number of trials, and p is equal to 0.4. This is 40% probability of success. And then we say samples is equal to, for example, 1000. We want to go for 1000 number of simulations. Then we generate binomial random samples. For example, we can say data binom dot random variables np and size is equal to samples. Then we can print our data, right? So this is like you can see 1000 samples, 1000 samples. So in here, each data is simply the number of sixes n equal to 10 independent Bernoulli trials, where each trial has a success probability of 0.4. Since we are drawing 1000 samples, in here our data contains 1000 realization from binomial distribution like n10 and p of 4. So then we go for mean. So mean is simply mean is equal to np dot mean of our data. Also, we can go for the variance. Variance is equal to np.var of our data. Then we can print them, right? We can say print if sample mean is equal to mean.2f 3.93 and sample variance print if sample variance is equal to var is 2.4, and this is the simulation, but in theory we had something different, right? A little bit different. So we can say if theoretical mean is n multiply p, which is 4, and print if theoretical variance is it is n multiply p multiply 1 my p. So you can see it's a little bit here different. It's because of the simulation. We can also plot this one. You can plot histogram of simulated data. So we can go for plotting, plot figure size 3 and 3, then plot histogram, means range of n plus 2, h color black, alpha 8, and also we can add here density is equal to true, and also we can add a label as simulated, right? Then we can go here and we make some x as np.a range of 0 and n plus 1, and then we go for PMF. PMF is equal to binom dot PMF. So in SciPy we have this function and we will pass x, n, and p. Then we can plot plt dot plot x PMF. Then it can be something like this, ro dash, and for label we can say, for example, theoretical PMF. Then we can add the title to it, for example, plt title if binomial distribution of n and p with p, then x label number of success, y label probability, legend also we add it, grid also we add it, and we print it. So you can see here, this is the representation of the simulation that we had. These are the number of sixes. So, and here we can see the probability. In our example, we say that 40% in each 10 trial, right? So you can see here, most of them is here close to number of is close to 4, right? Then it reduces in these two sides. So this plot resembles a binomial of 10 and zero point 0.4 distribution. This is, you can see most of the data is close to expected, which is 4. The most frequent values are around 4 and 5 here, with fewer occurrence close to 0 or 0, 1, and 9 and 10. Also, we can plot PMF for different p-values. For example, we say p-values equal to, for example, 0.2, 0.5, and 0.8. And then x, we make x for the x values NPA range of 0 and n plus 1. Then we can plot it. So plt dot figure, and you can say size 3 and 3. Let's make it a little bit more, 5 and 5. Then here we say for p in p-values, PMF is equal to what? Binomial of PMF, then we will send X, N, and P. Then we say PLT plot X PMF, and representation can be O and dash, and label is equal to F, and we can say P is equal to P, and also we can say marker size is equal to 8, right? Then we can print it, right? So let's change this one to 3. Okay, and also let's add the legend to understand what happens. Okay, so you can see here for probability of 0.2, you can see the blue one, the most of the data are here. For probability of 0.5, most of the data are close to here. And for P, probability of 0.8, most of the data are here, right? This is how binomial works. Let's see what the example here. Each of 6 randomly selected cola drinkers is given a glass containing cola S and one containing cola F. The glasses are identical in appearance except for a code on the bottom to identify the cola. Suppose there is actually no tendency among cola drinkers to prefer one cola to the other. So we can say P is equal to probability of a drinker prefers S is equal to 0.5, right? And here we have X as the number among the 6 who prefers S. So our random variable follows binomial of 6 and 0.5. Okay, binomial distribution where n is equal to 6 and p is equal to 0.5. So the PMF for this example is, we write b x 6 and 0.5 is equal to combination of 6 and x, 0.5 in power of x, and 1 minus 0.5 is 0.5 in power of 6 minus x. So x is what? X is equal to 0, 1, 2, up to 6. Then the probability that exactly 3 prefer S, we write probability of x is equal to 3 equal to binomial of 3 and 6 and 0.5, which is equal to combination of 6 and 3, 0.5 in power of 3, 0.5 in power of 3, which is equal to, so we will calculate this combination, right? How we calculate 6 factorial divided by 3 factorial, 6 minus 3 factorial, right? So it will be 6 factorial multiply 5 multiply 4 multiply 3 factorial divided by 3 factorial, 3 factorial, right? So this we cancel out, and this will be 6. So 6 by 6 will cancel out, so it will be 20. So it will equal to 20 multiply 0.0 in power of 6, which give us 313. Right, the probability that 3 or more prefer S. So we write probability of x greater than or equal to 3 is equal to sum of x is equal to 3 up to 6 binomial of x 6 and 0.5, which is equal to sum of x is equal to 3 to 6, combination of 6 and x, 0.5 in power of x, 0.5 in power of 6 minus x, right? And if we do all these calculations, right, each time, so one time you calculate for 3 like I did for the previous one, next time you do it for 4, next time for 5, and next time for 6. And if you do all this calculation, then you will get something, right, 0.656. Probability that one or fewer prefer S is probability of x less than or equal to 1 is probability of only x is equal to 0 up to 1, right? Binomial of x, 6 and 0.5, right? So once we put 0 here, once we put 1 here, right? And based on the 3 that I calculated, it will be 0.109, right? So let's do the same in Python. So I suppose that already we imported NumPy and we already imported binom from SciPy stats. So in here we say n is equal to 6 and probability of sixes which prefer cola S is equal to 0.5, right? Then we calculate probability for x equals to 3, right? So what we do, we say P3 is equal to binom dot PMF, and in here we say 3n and P. It will compute PMF for x equal to 3. Then we calculate probability for x greater than or equal to 3. We can go for survival function. This survival function is simply 1 minus CDF, and it represents the probability that a random variable x takes on a value greater than x, right? So this is called as survival function. So for p greater than or equal to 3, we can go for p greater than or equal to 3 is equal to binom, and the name of the function of survival function in binomial is SF, and in here we say 2n, n and p, right? Then we can calculate probability for x less than or equal to 1, right? Cumulative probability. So we can say probability of less than or equal to 1 is equal to, for this one, first we need to generate some x values, right? So we say np dot a range of 0 and 2. This apply x values from 0 to 1. Then in here we can say binom dot PMF, and in here we can say x values n and p, right? This one, binomial PMF, this is PMF. So let's say here PMF here, and then we say probability of less than or equal to 1 is equal to NP sum of those PMF, right? Sum of these PML that we have generated here, right? This is how we do it. So we can print them. We can print them. Like in here, we can say print P3.2F, right? 31%. Then the same thing we can do here for this one. It is 66%. The same thing that we can do here. And it is 11%. If you want to get exactly the same numbers, we can change this one to 313, then 656, and here 109. Then we can plot them. So our n was equal to 6 and p was equal to 0.5, right? And so we go for possible x values. So we say like x values equals to np.a range of 0 to n plus 1. Then we can say PMF values. PMF values is equal to binom of PMF, and then we will pass the x values and n and p. Then we calculate CDF values. So CDF values is binom dot CDF, and in here we pass x values n and p. Then we go for survival function. As I said, survival function is simply 1 minus CDF, and this is the probability that a random variable like x takes on a value greater than x, right? So we can say SF values is equal to binom dot SF x, sorry, in the here should be x values, and here should be x values and n and p, right? So then we can go for plotting. So plot figure and fig size is equal to like 5 and 5. Then here we can say plt dot bar and x values pmf values, color like blue, and alpha as the transparency is equal to 0.7, and label is PMF. Next we go for PLT plot x values and CDF, and we go for some presentation value CDF. Then we can say that plt.x label is equal to like x. Then we can say plt.y label is probability, and we can define a title for it. PLT title like binom PMF, where n is equal to 6 and p is equal to 0.5. Then also we can say PLT x as x values, and also we add a legend. Change it to 6 and 3. So this plot shows the probability mass function, this blue color, cumulative distribution function, red color, and green color is survival function for a binomial of, and what n was equal to 6 and probability was 0.5. We can say that success probability is 0.5, right? The PMF gives the probability of exactly x success in n trial. So in this case, each bar represents the probability of achieving a specific number of cola drinkers from 0 to 6. And the CDF specifically highlights the probability. It means the likelihood of exactly 3 out of 6 drinkers prefer cola. Next, we can go for bar plot for x is less than or equal to 1 compared to p greater than or equal to 3. So we can say PLT figure, and we can say fig size is equal to like 6 and 3. Then here we say bars equal to, we can say p probability of x less than or equal to 1 and probability of x greater than or equal to 3, right? Then we can say values equal to binom.cdf, and here 1 and p, and binom.survival function 2 and n and p. Then we can say plt.bar, bars values color is equal to, one can be red and the other one can be blue. Yeah, and the transparency alpha is equal to 0.6. Then we can say plt.y label as probability, and plt grid so here we see for x less than 1 and x greater than 3. So this compares to a specific cumulative probabilities. This comparison visually emphasizes how the probability of lower versus higher success differs in the binomial distribution. We can go for heat map like visualization. For this one, we will import Seaborn as SNS. Then here we can say plt.figure, and fig size is equal to like 6 and 3. SNS.heatmap PMF values dot reshape. We change the shape of the PMF values. Then annote is equal to true, and CMap is also equal to blues, and X tick labels is equal to X values, and Y tick labels is equal to PMF. Then we can print it. PMF values. Once again, I explain here what happened. So we imported Seaborn as SNS. In SNS or Seaborn, we have too many kind of plots. So this function heat map generates heat map. It's a kind of color-coded representation of data. Then we get PMF values and we reshape 1 by -1. So we reshape this array into one row matrix. It's a kind of single row 2D array for visualization, because we want to PMF value are displayed in a single horizontal line. Then here we say annotation. These display the numerical values of PMF values within each cell of the heat map. We use this blue color map to visually distinguish different probability values, and then we go for x ticks. Here we assign x values as label for the columns, and in here we go for PMF, that ensuring only one label appears. So here you can see the plot. This is a kind of heat map like plot that visualizes the PMF value as a color gradient. The darker side of the color is the higher the probability for that value of x. It shows the binomial probability for each x, like from 0 to 6, with annotation of each individual probability values that each may have. So this is a kind of heat map that helps in quickly assessing which values of x have higher or lower probabilities. Let's see one example. If 75% of all purchases at a certain store are made with a credit card, and X is the number among 10 randomly selected purchases made with a credit card. So in here, our X follows binomial of 10 and 0.75. So we want to calculate the expected value. In here, expected value is equal to, based on the formula that we have, NP, which is equal to 10 multiply 0.75 is equal to 7.5. Then variance of X is equal to NPQ, and Q is equal to 1 minus P. So we say 10 multiply 0.75 multiply 1 minus 0.75 is 0.25, which is equal to 1875. Then standard deviation is simply root square of NPQ is equal to root square of 1.85875, which is equal to 1.37. Once again, I explain we have n trials purchases with the probability of 75% success, or you can say probability of using a credit card. Then the average number of success, it means credit card purchases per experiment is 75. So then the probability that x is within one standard deviation. What is the probability that x is within one standard deviation? What it means? It means the probability of x between, right? So we say expected is 7.5 and standard deviation is 1.3. It means 7.5 plus 1.37 and 7.5 minus 1.37, which is equal to probability of x between 6.13 and 8.87, right? Because our variable is discrete, simply we can say probability of x is equal to 7 or 8, right? So, and it is probability of x is equal to 7 plus probability of x is equal to 8, right? So here we need to calculate probability of x is equal to 7 or x is equal to 8, right? So for probability of x is equal to 7, based on the equation, we say combination of 10 and 7, 75% in power of 7 and 25% in power of 3. The same thing, probability of x is equal to 8 is equal to combination of 10 and 8, probability of 0.75% in power of 8, and probability of 25% in power of 2. If you do this calculation, finally you will come up with 0.53 and 2. Let's do the Python coding for the same example. So I suppose you already imported NumPy and Binom from SciPy stats. In here, our n is equal to 10, p is equal to 0.75%, and q is simply 1 minus p, right? Then we calculate mean. So mean is equal to n multiply p. Variance is equal to n multiply p multiply q. And standard deviation is equal to np dot sqrt of variance, right? Then we want to go for bounds for one standard deviation. So we say lower bound is equal to mean minus standard deviation, and upper bound is equal to mean plus standard deviation. Then we want to calculate probability of x is equal to 7 and x is equal to 8, right? Then we say probability of 7 is binom of PMF 7, N, and P. And P8 is equal to binom dot PMF 8, N, and P, right? Then we get sum of them. P, 7, and 8 is equal to probability of 7 plus probability of 8. Then we can print them, right? So we can say print f mean is 7.5. Then the same variance, print f var 1.88. Then standard deviation, print f std 1.37, right? Then we go for our lower bound and upper bound. So lower bound, upper bound, right? Then we can go for probability of 7 and 8, right? Probability of 7, probability of 8, and probability of 7 and 8. 0.53. For plotting, we need to have x values NPA range 0 to n plus 1, and also we need to calculate PMF values of these x values based on n and p that we have. Then we can make plot based on this one. So plot plt.figure and fig size is equal to 6 and 3. Then here plt.bar, and here x values, PMF values. It's okay, this one is okay. Then we can go for plt.axv line, and we say here x is equal to 7, color is equal to red, line style is dashed, and label is equal to x equals to 7. This AXV line, this is used to draw a vertical line across a plot at a specific x coordinates. Then we can do the same thing for 8. So we can say x is equal to 8 and color green, and here x is equal to 8, right? Then the same thing we can do for lower bound. So in here we say x is equal to lower bound, color is, for example, orange, life is, and in here we change it to lower bound. Then the same thing for upper bound. Upper bound color is orange, and here we say upper bound. So let's here do it. Okay, here we go. This is our plot. This plot visualizes the probability mass function PMF for a binomial distribution, and in here our n is equal to 10 and our p is 75%. This red line that you can see here is the probability of x is equal to 7, and this green dashed line is probability of x is equal to 8. This orange line that you can see here, they are called as lower bound and upper bound. They are one standard deviation from the mean. These boundaries give us an understanding of how much the distribution spread is around the mean. Thank you very much for your attention. This was an introduction about binomial distribution. Please practice and feel free to ask me if you have any questions by leaving a comment below this video. Thank you and see you in the next lecture.